Good morning, everyone. I will continue discussion of star formation rates in galaxies, although I will be talking about larger scales of entire galaxies. So we can define a time scale on which a galaxy would convert all available gas into stars at a given star formation rate. And for typical star forming galaxies, these time scales are extremely long. So depletion times are the order of billions of years. And it was not clear why these depletion times are so long. So for example, here is the concluding slide from the Andy Bruecker's talk from the last year, which actually partially motivated our work. So thanks. And the conclusion there was that the origin of depletion times is a mystery. So it's mystery because the depletion times are substantially longer than any other time scale relevant for ISM. For example, dynamical time scales such as turbulent fluorescent time on a disk scale height, typical freefall times in the ISM, or even orbital period of a galaxy on which global instability is developed. All these time scales are orders of magnitude shorter than the depletion time, even if you consider only the molecular phase of the ISM. So this means that globally star formation is extremely inefficient. Usually this global inefficiency, actually sometimes this inefficiency is explained by local inefficiency. So as we know now, star forming molecular clouds form only about, convert only about few percent of gas into stars over freefall time. And this means that if we look at the the total depletion time in such clouds, we'll get the time scales of order of hundreds of millions of years. However, this is still not enough to explain the global depletion times. And we formulate a very simple conceptual framework where we can explain both discrepancy with dynamical time scales and with the local consumption time scales. And we formulate this framework based on insights from simulations, which I briefly described here. So we model Milky Way-like isolated galaxy with ARC code using subgrid models for heating, cooling, self-shielding, and feedback calibrated on simulations of supernova remnants evolution. And what is peculiar about this simulation is that we use a dynamical model which allows us to predict subgrid turbulence velocities. And I won't go into details here, so we can look at the original paper or into our paper last year, or you can talk to me afterwards. But the idea is that we can model the distribution of local turbulent velocities, and therefore we can predict resolution scale distribution of viral parameter, and models of star formation in GMCs predict that the efficiency is a strong function of viral parameter. So we can take this into account in our simulation. And here's the result. So shown are density, temperature, and turbulent velocities, and galaxies. So galaxy forms the thin disk with the complicated multi-phase structure. And in terms of the global star formation, it nicely fits observed values in Milky Way and nearby spiral galaxies. So we can go into simulation and ask why depletion times are so long. So in order to do this, it's illustrative to consider gas distribution in a plane of density and total velocity dispersion, which includes both thermal motions and turbulent motions. So this is very similar to density temperature diagram, which would look like this. However, in this case, velocity dispersions in the cold gas are dominated by subgrid turbulence. So higher velocities means higher, stronger support, and therefore star formation rates are slower. On the other hand, if we go to higher densities, star formation rates becomes larger, higher, and overall viral parameter decreases along this direction, and efficiency exponentially increases. So for simplicity, we assume a sharp threshold and allow gas which falls below the viral parameter of 10 to form stars at the efficiency of 1%. And now distribution of this gas determines the global star formation rate of the galaxy. And the total mass of this gas is, so as we know, mass conservation should work, and the total gas is changing due to total flux through the boundary, and also due to gas consumption in the star forming state. In general, it's not necessary here to assume equilibrium, and in paper we consider the general case, but this galaxy settles into equilibrium where the total mass of star forming gas remains approximately constant, and this means that the star formation rate becomes equilibrated by the total flux. So now we can rephrase our original question, why galaxies form stars slowly, why star formation rate is slow, to why the total flux is small. And we can do this in simulations with the aid of passive gas tracers. So we can measure the actual flows of gas on this diagram and the actual average flows. And we see that those flows are indeed quite slow, consistent with long depletion times. However, if we look into details, if we separately consider positive flux that supplies gas into star-forming state due to gravity, cooling, and compression, and negative flux, which removes gas by feedback and dynamical expansion of gas, we will see that these fluxes are way more stronger than the average flux, but at any given point, they cancel each other, resulting in a small net flux and long depletion time. So in order to understand how galaxy can maintain such strong fluxes on the time scale of galaxy evolution, we can look at trajectories of individual gas parcels in the ISM. So if you were an atom in the ISM, this is more or less what you would do. The trajectories of individual gas parcels, they are very complicated in this diagram. So it's the same diagram that I showed before, and gray contours show the same distribution. And you see that gas parcels don't go to the star-forming state and stay there until they are converted into stars. Instead, they're going back and forth in a rather short time scale. So the gas evolution is cyclic. And if we look at the time evolution of the real parameter, we can see that the time scale needed to perform a single cycle is rather short. It's of the order of hundreds of millions of years. And only a small fraction of this time is actually spent in the star-forming state. So because of this, because each gas parcel spends only a small fraction of time in the star-forming state, and because star formation in the star-forming state is inefficient, because of this, on each individual cycle, only a tiny fraction of gas mass is converted into stars. As a result, a large number of such cycles would be required to convert all the gas into stars. And actually, so the total time, in order to be depleted into stars, each gas parcel needs to spend one depletion time of star-forming gas in the star-forming state. And if we divide this time by the typical duration of the star-forming stages, we can figure out the average number of cycles required for gas to be depleted. So now we can trivially express the global depletion time as a number of cycles multiplied by the average duration of each individual cycle. And this expression shows that the depletion time is long because a large number of cycles is required. So for typical durations of star-forming stages, we find that on average, gas parcels go back and forth on the order of tens and hundreds of times. In addition to explaining why depletion time is long, this expression also allows us to predict and how depletion time should depend on different properties of galaxies. So for example, it explains why in galaxy formation simulations, depletion time or star formation rate becomes independent of star formation efficiency if the feedback is efficient. So in this case, what efficient feedback does, it regulates the duration of individual star-forming stages, because now they are limited. So now the lifetime of gas in star-forming state is limited by the time on which feedback destroys the region, and this time is proportional to this time depends on the rate of momentum and energy injection by new stars, and which is in turn proportional to the star formation rate. So as a result, the duration of star forming stages becomes proportional to the local depletion time of star forming gas. And this means that in the expression for the total number of cycles, dependence on the efficiency disappears. So now the number of cycles doesn't depend on efficiency. Now, if we assume high enough efficiency, then the time that gas spends in the star forming state, this tau star, becomes much smaller than the time spent in the non-star forming state, and the depletion time becomes dominated by this first term, which does not depend on efficiency, and this is indeed seen in simulations. On the other hand, the duration of the star forming stages is still depends on the amount of energy momentum injected by each individual supernova, strength of feedback. So, and this is indeed seen in the simulations, as was nicely shown by Phil Hopkins' group. when you change the feedback strength, then in this self-regulated regime, the total star formation rate scales with the strength of feedback. So to conclude, we formulate very simple conceptual network framework, which explains why depletion times are long. So first of all, they are much longer than the dynamical time scales because a large number of dynamical cycles is required to deplete all the gas in the galaxy. On the other hand, it's the depletion time is also longer than the local consumption time because in addition to time spent in the star forming state, gas spends some time in the non-star forming state. So majority of time is spent in non-star forming state. This simple equation allows us to make predictions about how depletion time depends on different properties of galaxies because different terms here depend on different physics. And as an example, I showed you how this framework explains self-regulations in galaxy simulations. Thank you.
Thanks very much. Questions?
Can you say a little bit more? I'm sorry if I missed it, about how the feedback happens in this model. How does that drive the
basically, whenever supernova explode, we inject thermal energy and momentum. So it's, yeah, and so this momentum destroys the region. Yeah, in particular, yeah, and also it sends like large scale wave which destroys the region itself. Restart.